Okay, we're going to look at reaction profiles or reaction energy profiles. So if you just look at this graph on the left, I've written down chemical energy on the axis there. Usually they just write energy, but I like to think it is chemical energy. And of course, what happens in chemical reactions is that chemical energy is converted into heat energy or vice versa. They're the two energy stores we're talking about here, the chemical store and the thermal store. Right, so here we've got reactants and they've got more chemical energy in them than the products, so that must be an exothermic reaction. This much energy, this much chemical energy is turned into heat energy, so this is the heat energy released. Okay, and this is an exothermic reaction. The one on the right, well, the products have got more chemical energy in them than the reactants, so this is an endothermic reaction. And this line here, the green line, that is the heat energy converted into chemical energy, so the heat taken in, and that's an endothermic reaction. Right, now we need to think a little bit more in detail what's going on here. So we're going to actually look at a real chemical reaction. We're going to look at the reaction we looked at in the bond energy calculations video, the reaction between hydrogen and chlorine to form hydrogen chloride. You can see there now. So remember that when we break a bond, that we need to put energy in. That is, breaking a bond is endothermic. And when we make a bond, that's exothermic, we get heat energy out. Right, so somehow we've got to get from over here, where we've got the hydrogens bonded to each other and the chlorines bonded to each other, to this situation over here, where you form new bonds between the hydrogen and the chlorine themselves. So it's pretty obvious that at some point in between there, the old bonds must break, and you must end up with hydrogen atoms separated from each other and chlorine atoms separated from each other, and then the new bonds form and you form HCl. So let's think about what happens there. Well, this, in terms of energy, this first stage here, this is endothermic. So you take in heat energy, it's converted into chemical energy. So you can probably see then that the hydrogen atoms and the chlorine atoms by themselves, they've got very high chemical energy. They've got a lot of chemical energy. To get to that stage, you've got to take in heat energy to break the bonds. And so in this next step of the reaction, where we form new bonds, that's exothermic, we get the high chemical energy in these two is turned back into heat energy, and we get our products. So let's see what the graph of that would look like. So here we have our graph. I'll just make it a bit bigger, so you can see it looks a bit different to last time. Right, so we started off here with here are our reactants, and with a lower energy, here are our products. Now we can see before the reaction goes, a certain amount of energy, a certain amount of heat energy must be taken in and converted into chemical energy in order to break the old bonds. Now that energy is that much there, and that is called the activation energy of the reaction. And if the hydrogen and the chlorine collided with each other quite slowly, and they didn't have enough kinetic energy in order to break those bonds, then they just bounce off each other. The only time they react is when the collision has an amount of energy equal to or greater than the activation energy. So it's the minimum amount of energy molecules must have in order to react. If they don't have that, they just bounce off each other. Okay, so that we need to be familiar with that term, activation energy. And look at this sort of state here, this intermediate state, where it's got a lot of chemical energy. It's got high chemical energy there. And to get to there, some of the kinetic energy of the molecules, which is basically the heat energy, isn't it? How fast they're moving, has to be converted to break those bonds to get to the high energy state. Now we look at the overall amount of energy released. Well, you can see the amount of energy released is that. So that is the energy released in this reaction. You may think, well, why isn't it that, the yellow line I've just drawn there? Well, it's not that, because you have to put in the activation energy to get it going. You do get that back, but that's not the net amount of energy that you get. The net amount of energy, the overall amount of energy, is the green line. Okay, so let's just look at that in a more general term. So that was that particular example. You need to be familiar with these little graphs, and they're called reaction profiles, and they have that little hump in them there, and that is the activation energy. So if let's just make that a bit bigger. Now the one on the left you can see is an exothermic reaction. How do we know that? Well, we know that because if you look, the energy of the reactants, chemical energy of the reactants, is higher than that of the products. So you get the blue line there, that's the net amount of energy released. And this red here, this is the activation energy. Let's look at the endothermic on the right hand side. You can tell it's endo because look, the reactants have got less chemical energy in them than the products have. And so that amount of energy, that's the net energy taken in. Now let's think, what is the activation energy of that? Well, a lot of people sort of think, oh, it's that, it's just that, but it's not, of course, because the amount of energy you have to put in to, to get up to this high energy, high chemical energy intermediate state here, well, it's all of that. That is the activation energy. So that's the diagram for an endothermic reaction. Now, in exam questions, they show you one of these profiles, and they'll ask you to label the activation energy. Maybe it'll be an endo, maybe an exo, and they'll ask you to label the energy released or the energy taken in. One last thing we need to talk about is we need to talk about how do catalysts work. So I'm just going to tidy that up a little bit. Right, and how a catalyst works is what it does is it lowers the activation energy. So with a catalyst, the activation energy of the reaction might just be there, okay, the green line. So the activation energy with the catalyst is just that little bit of energy there. So, well, how does that work? Well, it means that because the activation energy is lower, it's more likely when molecules collide that they've got enough energy, the energy greater than the activation energy, to enable them to react. So rather than just bouncing off, they do have enough energy. The energy of the collision is greater than the activation energy, so they can react. So another very common question would, they'd give you an energy profile, and they'd say, sketch on where's the activation energy when you use a catalyst, which would be the green line there. Okay, so that's that. So make sure you can know the shapes of those graphs, and you can label activation energy, energy released or energy taken in, and be able to mark what effect a catalyst would have.